If you'll notice the progression, we've been calculating various properties of the channel so that the walls and the bottom of the channel would be stable. In this particular example, we're going to know the properties of the sediment, and we're going to determine the critical velocity above which the sediment would move. So we're going to have water at 20 degrees Celsius. The method we're going to use is called the Couligon's equation. And our example is for a wide, shallow channel, which I mentioned before. A wide, shallow channel has the hydraulic radius equal to the normal depth because the small amount of channel resistance on the edges is neglected. So for water at 20 Celsius, the density is 998 kilograms per cubic meter. The dynamic viscosity mu is 1 times 10 to the negative third Newton second per meter squared. The kinematic viscosity nu is 1 times 10 to the negative sixth meters squared per second. The sediment property is the D50 is 2 millimeters, which is a very coarse sand, and the depth of flow will be 3 feet. Now the equivalent sand roughness, K sub S, is going to be 2.5 times D50. If you recall from fluid mechanics way back when, the concept of the equivalent sand roughness was utilized on the first experiments involving pipe friction. So the equivalent sand grain roughness ordinarily goes from 1.4 times the D84 to the 3.5 times the D84. The hydraulic radius is R sub H, and the specific gravity is 2.65 normally for the sediments. The equation for the dimensionless sediment number, or particle size, is the ratio of the sediment specific weight divided by the water specific weight minus 1 times g times d cubed divided by nu squared to the 1/3. Once you get the d star, you use d star and figure 10.6 to get tau star c, which is the dimensionless critical shear stress. Figure 10.6 is similar to one of those Shields diagrams which I showed you earlier. After you get the critical dimensionless shear stress, you use Couligon's equation, which is given below, to calculate the critical velocity for stable channel walls and bottom. So if we look at this particular version of Shields diagram, and we would come in with our dimensionless particle size or sediment parameter, we can then determine the value of the dimensionless critical shear stress. In this case, we would want one of the lower curves, for example, the occasional particle movement at some locations or the frequent particle movement at some locations, because we are more interested in when do the particles start moving. So for our particular dimensionless sediment diameter, it comes out to be 50.59. That gives us a critical dimensionless shear stress of 0.023. Our hydraulic radius is 0.91, and putting that in gives us a critical velocity of 0.52 meters per second, and the Froude number at the normal depth of being 0.18. This tells you that if the velocity in the channel exceeds 0.52 meters per second, you can expect erosion to occur. This would be another diagram that we could use in order to solve this problem. Coming in with a dimensionless sediment size and then getting the dimensionless critical shear stress off the vertical axis.